Singleton is usually summarized as one instance with global access. That shortcut hides the question that makes the pattern useful or dangerous: one instance inside which owner? A desktop application, a service provider, a browser tab, and a server process are different boundaries. None of them guarantees one object across an entire machine or cluster. The pattern coordinates identity and lifetime inside a chosen boundary. Repeated access reaches the same object. Clients do not create competing copies, and one owner decides when that object is created and released. In this episode, we will compare the classic self-owned form with a lifetime managed by .NET dependency injection. Then we will build the second form from empty files and prove exactly where its guarantee ends. 4 decisions travel together. Identity means 2 requests return the same object reference, not merely equivalent data. Lifetime defines how long that reference stays valid. Access describes how clients receive it without quietly becoming its owner. Shared safety covers everything that follows from reuse: concurrent callers, mutable state, memory retention, and cleanup. A singleton can be created eagerly or on first use. It can be exposed through a static property or supplied through constructor injection. Those are implementation choices, not the intent itself. The invariant is simpler. One owner manages one shared identity for its lifetime, and every participating client agrees to that boundary. The classic form makes the type its own owner. A private ordinary constructor blocks outside construction, a static member stores the instance, and a static property exposes it. That shape can be correct, and the private constructor is a legitimate exception to a primary constructor preference because accessibility is part of the pattern. It also creates global access and couples every caller to the concrete type. With dependency injection, the service stays an ordinary class. The service provider becomes the owner. A singleton registration defines the lifetime, and clients ask for an abstraction through their constructors. That is the model we will implement. We are not making Star Catalog a self-owned singleton. We are giving it one lifetime inside each provider. Singleton fits when construction is meaningfully expensive. One immutable snapshot should serve many consumers, or an owner needs one long-lived connection to a resource designed for concurrent use. It also works for stateless services whose identity is unimportant but whose setup is costly. Do not choose it because one allocation feels tidier. User state, request state, and unit of work objects usually need shorter lifetimes. Shared mutable data needs its own synchronization. The container cannot add that for you. A singleton that captures a scope dependency quietly extends that dependency to the root lifetime. It can also keep a large object graph alive until shutdown. And because every process owns separate memory, singleton is not a distributed lock. The lifetime needs a concrete reason and a boundary you can name. Our example is a small observatory planner. A star catalog turns source records into a case-insensitive frozen index. Building it twice gives correct results, but it repeats the same construction and leaves lifetime ownership scattered among callers. The catalog is a sensible sharing candidate because its data is complete before publication, and every later operation is a read. Observation Planner is a consumer, not an owner. Program is the composition route where we can compare the direct approach with a provider-managed lifetime. The question from the theory now has a concrete answer: one star catalog inside one service provider. We start with the data and the contract. As star record appears, its primary constructor names the 4 values the planner needs, and the sealed record gives us value semantics without ceremony. iStar catalog is the surface consumers depend on. Count lets the terminal prove how many records were indexed, while find expresses the one lookup the planner needs. There is no static instance property and no container reference in this file. The abstraction says what a catalog can do. It says nothing about whether the implementation is transient, scoped, singleton, or replaced by a test fake. Now, star catalog takes the source records through a primary constructor. That syntax is available because this container-owned model does not need a private constructor. The class remains sealed because inheritance adds no useful variation to this concrete index. Create index runs once for each star catalog object and returns a frozen dictionary keyed by name with ordinal, case-insensitive comparison. The field is ready before any client receives the service, and count only reads it. This is where the example earns a shared lifetime. The index has setup cost, then becomes stable. AddSingleton will control how many star catalog objects a provider creates. Nothing inside this class claims process-wide uniqueness. Find accepts a name and uses one conditional expression for the valid path. A blank name or missing key becomes a clear key not found exception. Create index guards the incoming sequence, builds the frozen dictionary, and rejects an empty result. Notice what these checks protect. They make every constructed catalog valid. They do not create the singleton lifetime. That distinction matters because the same class can appear in our direct baseline and later in the container-managed version. The cursor moves with the helper, so the exception and its parameter name are visible before we discuss them. We never need a code selection to make the relationship clear. Observation Planner receives iStarCatalog through its primary constructor. As catalog is typed, the name identifies a collaborator, not a global service to locate later. The field rejects a null caller and keeps the dependency available to plan for. The method asks the catalog for 1 star and returns a culture-invariant observation line. The planner does not know who constructed the catalog or how long it lives. That ignorance is useful. Production can choose a singleton lifetime, while a unit test can pass a small fake or a fresh instance. Lifetime belongs at composition, not inside the consumer. Program begins with 3-star records. The collection expression is concise C#14 syntax, and the I-read-only list type makes the intended input clear. We then construct first catalog and second catalog directly from the same records. Both objects are valid and contain equivalent frozen indexes. The planner receives the first one and produces the Vega observation. Finally, reference equals asks the identity question rather than comparing data. This baseline is not deliberately bad. Direct construction is often the clearest choice. Here it gives us observable evidence that 2 callers can independently create the same expensive snapshot and that no owner has declared a shared lifetime. The baseline runs successfully. Vega is found, the catalog contains 3 entries, and direct construction reports false for shared identity. That last line is not a domain failure. It is the design pressure we wanted to expose. 2 correct catalogs exist because each caller chose construction for itself. We now have a behavioral reference point and an identity result to compare after the lifetime moves into one owner. Read program as an ownership map. It knows the source data, chooses when both catalogs are constructed, and passes one into the planner. Star catalog is already focused. It validates records, builds an index, and serves lookups. Making that class expose a static instance would add global access and force it to discover the application data. The missing responsibility belongs in the composition root. Programs should decide that this catalog is shared, but clients should not perform the construction themselves. We will keep the domain types unchanged and replace scattered creation with a provider that owns the lifetime. We rebuild program as the composition root. The seed records stay because the application still owns its input data. The new services variable is a service collection, a set of lifetime and construction descriptions that has not created our catalog yet. This is an important pause. A container is not the pattern by itself. It is the owner we have chosen for this application boundary. The next registration will connect iStarCatalog to StarCatalog and state how long one instance should be reused. AddSingleton registers a factory for iStarCatalog. The first resolution from a provider calls that factory with our seed data. Later resolutions from the same provider return the same object. Observation Planner is transient because each planning operation is cheap and has no reason to share identity. Validate on build and validate scopes turn composition mistakes into early failures, including a singleton that captures a scoped service. We build 2 providers only to test the boundary. A real application normally builds its root provider once. These 2 owners use the same registrations and source data, but each owns its own singleton cache and disposes container-created services when the provider is disposed. Now, first catalog and same provider catalog are resolved from first provider. The names state the claim before the terminal proves it. Other provider catalog comes from the second owner. Observation planner is also resolved from first provider, so constructor injection supplies that provider's IStar catalog without the planner calling getRequiredService itself. This is not service locator code inside a domain class. Resolution remains at the application edge. The output preserves the successful observation and count, then asks both identity questions. Same provider catalog should be the same reference. Other provider catalog should not. One registration gives us a precise, testable boundary rather than a vague promise of one object everywhere. The final run keeps the domain behavior intact. Vega still resolves and the catalog still contains 3 records. The same provider reuses its singleton, so the first identity check is true. Different providers own different instances, so the second check is also true. That pair is the lesson's real result. AddSingleton gives one instance per service provider registration. It does not prevent another provider, another process, or direct construction from creating another star catalog. The container safely creates and resolves the singleton, but it cannot make the service's mutable operations thread-safe. Our frozen index avoids that problem because construction finishes before sharing, and every later call is a read. A singleton must not capture a scoped service, such as a request DB context. Scope validation helps catch that lifetime leak. When the provider creates a disposable singleton from a type or factory, the provider disposes it at shutdown. An instance supplied from outside keeps its original owner and disposal responsibility. Tests should create isolated providers instead of resetting global static state. Long-lived services also retain their object graphs, so size and stale configuration matter. Finally, a singleton lives in local memory. Coordinating work across replicas needs an external store, lease, queue, or distributed lock, not this pattern. Rebuild the pattern from the owner outward. Service provider is the boundary. AddSingleton defines the lifetime. Star catalog is the one instance inside that owner, and observation planner receives it as an explicit dependency. We proved the direct version first, moved only the lifetime decision, and then proved same owner versus different owner. Use singleton when one shared identity has a clear reason, a safe implementation, and a boundary you can name. Avoid it when global access hides dependencies or when shorter-lived state is the honest model. The useful question is not, how do I make one object? It is, who should own this lifetime?